Here we are again in the simulator. In the upcoming project, you'll apply a perspective transform to the camera images coming from the rover to shift them from the perspective seen from the rover's camera to one where you're looking down on the world from above. To do this, we'll use a reference grid that you can open up in the simulator by hitting the G key. Okay, so now we have a grid, and the way it's set up, each grid cell represents 1 square meter. If you zoom way out, you can get a feel for the scope of the map you'll be building in the project, where each pixel will correspond to 1 square meter on the ground. I've positioned the rover in front of one of these grid cells, so now I can see what the camera view looks like. To perform the perspective transform, you'll need to identify the 4 corners of a grid cell in the field of view of the camera. These 4 points will be your source points, or the points that define a square meter on the ground plane in the image. You'll then define the destination points, or in other words, the 4 points that will define that same square meter in a top-down view of the world. With your source and destination points defined, you're ready to use OpenCV to perform a perspective transform. This operation will transform your rover camera images from this perspective into a top-down or map perspective. Let's see how this works in practice in a Jupyter notebook. Here, I'm first going to invoke this matplotlib notebook command to allow me to investigate the images I'm plotting in the notebook. Next, I'll import OpenCV, NumPy, and some matplotlib packages to read in an image. So I've recorded some data and chosen this image as my calibration image, where I'm going to identify the pixel positions of the 4 corners of the grid cell in front of the rover. Let's have a look at it. Now I can move my cursor over this image, and at the bottom you'll see the pixel positions of the cursor as well as the RGB pixel values. This is how we're going to get the source points for the perspective transform. Record the values for X and Y of the pixel positions of each of the 4 corners of this grid cell. These 4 points define what a square meter on the ground looks like from the perspective of the rover camera. Next, we need to define where we want that same square meter to appear in our destination image. First, I'll define a function that uses the OpenCV functions getPerspectiveTransform and warpPerspective to do the heavy lifting. If you want to dig deeper into the math behind this method, check out the links in the lesson following this video. Essentially, we'll use getPerspectiveTransform to calculate the perspective transform matrix, M, and then apply that matrix using the warpPerspective function to generate a warped image. Here, I'm defining the source points as the pixel positions I found in the original image that marked the corners of the grid cell. I'm also defining the destination points, or where I want those source points to move in the final image. When I run this code, I get this result. Now, that original grid cell that appeared in front of the rover has been moved to here, and we now see it from a top-down perspective, so it appears as a square. Not only that, but all the other grid cells appear as squares as well. So we've succeeded in constructing a top-down or map view of the world.